Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
This is episode 13, season number 3. We're broadcasting live from the University of North Dakota here in Grand Forks. We do have a chat feature that's running, so if you have any comments or questions that you'd like to ask us throughout the podcast, feel free to use that feature. The other thing, of course, we always mention is our disclaimer.
Our disclaimer.
You want to do the honors
Okay,
today?
I'll do the honors this week. Anything said in this podcast or the opinions of Wayne, myself, or our guest, who we'll introduce in a moment, they are not the opinions of the University of North Dakota, the Department of Arts and Science, the College of Arts and Sciences, and the Department of Physics and Astrophysics. So it's just us on the hook.
Yeah, we're the only ones.
Yep.
And the other thing to note is we are also on Spotify. So if YouTube is not your thing and you'd rather watch us on Spotify, just find us. We are there. So
We're somewhere.
Today, Robert, we have a very special guest.
Yep.
Dr. Bryce Christopherson, who's an assistant professor in the Department of Mathematics and Statistics here at the University of North Dakota. So first of all, Bryce,
How's it going?
Thank you very much for doing this.
Indeed.
Well, thanks for having me. This will be fun.
Now, I always wanted to get a mathematician cornered so I can ask him very extremely important questions such as, and this is seems like the question that all mathematicians get asked at some point throughout their life. So here we go, Bryce. You ready?
Okay, yeah.
Is
Bring it on.
math discovered or invented?
Oh, the classic. Yeah. It's a good one. I mean, yeah. So I think there's a big tendency for mathematicians to view things from this kind of jaded perspective, this kind of safe perspective of not wanting to seem too out there or crazy, like we're, rubbing crystals and having our, tarot read or something like that. But in some sense, I don't remember who said it. Someone said every mathematician is a Platonist during the work week and a formalist on the weekends, right? Everyone acts like these things are real, that there are groups or rings, like they're just things that exist in some sort of abstract Platonic realm, and we talk about them this way. And then if you're ever pressed on the issue outside of work, somehow it's all just abstract symbols, right? We all act like we're interfacing with the realm beyond, the outside place beyond, physics and reality where pure abstract forms live. We just act like that all the time. But, if you're ever pressed, it always seems a little safer just to say something along the lines of it's purely formal manipulation of abstract symbols according to predetermined rules. And that's the case. And so I guess in the sense that whatever sort of, symbolic representations of things that we've come up with, those are certainly created, right? In the sense that there's no specific reason, that the character we use for an A has to be that specific pictogram, right?
Right.
There's no specific reason it has to be that thing. Okay, fine. Yet all the same, the combinations of some number of distinct sounds, irrespective of how you want to pictorially represent them, do have some sort of underlying structure that is not something that we've built. It's something that does seemingly just exist in some sort of abstract,
Right.
Platonic realm beyond reality, and it like something behind the curtain pushing at it. You can sort of see its outline on whatever objects in the physical world manifest themselves according to that pattern or something. Right. That is, I think for the most part, mathematics is mathematics itself, the things mathematics talks about, those things are discovered, but are tools for bringing those things from some sort of an abstract world and making them manifest in this physical one. We create those, right? Those are invented. We invent the means for the discovered thing to manifest itself in this world with us, which sort of makes us sound like weird wizards or alchemists, right?
Well,
But I don't know. It feels like that's what happens.
I've often in labs explained this same idea to students, in that a table is an actual object. but that combination of sounds, table, is meaningless without us giving it meaning. So it's the same sort of
Yeah.
idea. There is a there is a real concrete thing behind it, but how we describe and work with that concept is completely arbitrary. So, or not completely
Yeah.
arbitrary. It's arbitrary within the rules we've set.
Yeah, yeah. And the strange thing is that there's like some level of non-arbitrariness that you can't get away from, right?
Right.
Like and that's like the spooky part of it, where it feels like, oh yeah, you know, there's these things, these mathematical objects that you can make manifest in the world, or like see their shape and structure by, like, you know, putting physical things in the world in certain configurations, whether they're like, you know, the matter in your brain allowing you to think about it, or like symbols on a page allowing you to formally describe them. You can sort of like, you know, like I don't know. I always think of it like there's something behind the curtain, right? And like, you know, you sort of push on it and you can feel like the shape of the thing, right? But there still is some sort of thing back there. There still is some sort of constraint.
Right.
I've often thought about what is mathematics about, and you know, you might go like, oh well, it's about, like, you know, it's about formal systems of, you know, you assume some things, what are consequences or something like that. But like, you know, getting to like, it's about the structure of objects, right? But I guess like structure itself, you can view it like a structure is like an object in its own right. And so to some sense, it's about objects. But the concession I can make is it's at least only about, as far as I can tell, about conceivable objects. Perhaps there are some objects which I cannot conceive of, which are, you know, you could not formally describe and would hence be outside the realm of mathematics. But if you kind of get down into that, then it becomes something very strange indeed, where you go, I guess the subject matter of mathematics is conceivable objects, right? You could say like the properties of conceivable objects, but like properties themselves you can view as an object. So I guess it's just conceivable things.
Right.
I don't really know a good way to describe what it's about.
And the other thing, so things that are not conceivable may become conceivable depending on who's thinking about it.
Right.
Perhaps so. Yeah.
And
I mean, there certainly is some kind of upper limit to what can be conceived of, right? At least, I don't know, over any sort of like fixed volume in the universe over some fixed amount of time, right? There's certainly objects that are too large to be described by, or you know, to manifest themselves into reality over like that finite volume, right? Like,
well, I always
an object that's so long to define, you couldn't do it with all of the.
I always put it like this: there's mass limits to how many neuron connections can be made in a human brain, so there is an upper limit to what can be put into and conceived by a human brain. Have we reached it?
Yeah.
Probably not even close yet. You know, but
yeah.
You know, another way you could think of mathematics is do a thought experiment, a life somewhere else, totally independent of Earth. What would they develop in terms of their mathematics?
And
it's a good question. Yeah. I've often thought about that too. I think most people do, you know. Would you end up with like you imagine that certain low level things would be hard to avoid, right? Like certain parts of like order theory or something, you know, it becomes difficult to do almost anything without, you know, imagining some things coming before or after other things, right? Like no matter where you are, there's at least like a, you know, seemingly, I imagine, maybe I'm wrong, I'm not a physicist, like some sort of like notion of time passing, right? There's some sort of innate ordering to things, and so I imagine that you come up with order concepts.
Counting,
there's innate notions of like closeness, so perhaps you get some sort of pieces of topology or like, you know, basic geometry, like, you know, like Euclidean nice stuff, basic, you know, metric space type property things. But yeah, I wonder, maybe not, right? Who knows? Different world, totally weird types of life or something like that. Maybe you go down an entirely different tree of it and it looks almost nothing like what we find.
Yeah, you'd think they'd have some type of counting system, right? If they could see the sky, they could count the stars at night. If they have individual pieces on their body, like body parts, or not like a complete sphere or something, right? Then you would count those. If there's more than one entity in your family-like structure, right, you would count those, like your children or offspring or whatever you want to call them. And so there has to be some type of counting system,
Right.
which isn't that historically, Bryce, where mathematics really developed from, is the need to count things?
Yeah, I guess, like a lot of, yeah, yeah. So I often, it depends. It depends. If you think of mathematics just as being about numbers, right? Um, but like there are also many mathematical concepts that come up far probably before numbers, right? Like I would say that animals that have no sense of numbers have a sense of like distance or closeness, right? Like things being
Oh,
near or
wow.
far,
Yeah.
and like there are many other think lots of animals have like a sense of like maybe not like time passing or something like that, but even just like bright and dark, right? Even basic like bacteria and stuff can respond to bright and dark, and so they're somehow responding to some sort of like an ordered structure on things, right? Like things being more or less than something, like brighter or darker, right? And so you get like very basic concepts very early, but I imagine like the form, like like the mathematics, like there are mathematical objects that can become manifest in the behavior of animals even at like extremely low levels, right? Like that are probably they're aware of if they have awareness. But like the formal description of mathematics itself through like symboling activities, yeah, I would say numbers, something like that. Maybe I imagine we had numbers before we had writing.
Right.
Perhaps it maybe like the formal symboling activities of mathematics start with some kind of like economic motivation, some sort of record
Right.
keeping, right?
I
Like
was
once
about
you
to
have to
say
start actually writing down sums.
the earliest writing I've heard of, and I may be wrong here, but the earliest I've heard people talking about is indeed counting grain in the silos, and
Yeah,
things like that, and the cattle in the field, and such as that.
So you're
So
blaming it on IRS.
I blame it on the IRS.
exactly. It's the credit
Blame the
system
tax
that
structure.
develops mathematics. Yeah.
Yeah, you
But
kind of. I mean, the other thing is you got to have time to think about this stuff. So society,
Yeah.
you think of different societies. If you're in a completely, hunter-gathering type society, who has time to think about whether two parallel lines near each other is going to remain parallel forever, type of thing? If I could extend it off to
yeah.
infinity, right? Who's got time to think about that if we're worrying about filling your belly and those kind of things?
Yeah, I don't. I mean, yeah, I don't know. I don't want to step into any sort of hairy territory or anything like that. But as far as I'm aware, I don't believe that like the uncontacted tribes of the Sentinel Islands have like independently rediscovered like Galois theory or something. Like, yeah, it is certainly a luxury good, right? Most mathematics is born of a certain leisure, right?
Yeah.
Yeah, I mean, it would you develop to the point where you need it for trade, those kind of things, right? Just get along everyday life, because people have this notion, and I run into these people all the time, and I'm sure you do too, where I didn't know there was math involved, or I wouldn't have done A, B, or C type of thing. And it's
Yeah.
like, and it's
Oh,
almost
get
as
that
if,
all the time.
yeah, it's like you got this wall that otherwise it would be there, and you wouldn't complain too much about it. But if somebody comes along and informs you, by the way, this is mathematics, and they're like, oh my God, right? They'll step
Right.
away from the wall as if it's contagious or something.
Yes.
Where does that mental block come from?
Oh,
I've got my
that's a
own
great
ideas there, but
question.
I'd love to hear his. Yeah.
Yeah.
Oh man, yeah. No, I mean, every math teacher has different ideas of it, but like you're right. People do hate math. Yeah. I mean, I think people like math as an idea, right? It's not like a beautiful mind came out and people were like, that movie's a piece of shit. Like I hate this movie. Like, people didn't like dislike things about math. People like the Science Channel and stuff like that. People broadly enjoy the idea of it. They just don't like doing it. And I think it's like math is the most unyielding judge of for most people, it's the most unyielding judge of their deficiencies that they encounter, right? It's a non-human judge of their deficiencies, right? Like if you are in an English class and you're a poor writer, your professor can be like, like, oh, I totally like I get it. Like, you have like there's like a lot more softness to it, right? But like in math, like it's just like it's wrong. Like you employed an approach that was wrong, provably wrong, like has no hope of working. You can potentially see maybe where they're coming from, and hopefully you can kind of encourage them and say like, look, I understand what you're trying to do, and I see like the motivation for it, and that's reasonable, and you shouldn't feel too ashamed or anything like that. But
But
most
it's
people
wrong.
just get used to feeling wrong all the time, and they hate it,
Right.
which
I
makes
had
sense.
not thought of
right?
that, but
Yeah,
yeah.
so it's like a binary thing. You're either right or you're wrong. There's no in between in
Yeah.
that sense, right?
There's no partial credit.
Yeah, I mean, on some level, like hopefully you can find ways to give partial credit and like recognize portions of the right thing. But yeah, like I also think people get really hung up on it because it's so tightly tied to your like socioeconomic status and success in life,
Right.
right? Like if you're pretty good at math, like it's not that hard to get a good job, right? But if you're pretty bad at math, like there's a number of good jobs that are kind of off limits to you,
Okay,
right?
so let's
And
let's use what you just said. You're pretty good at math or you're not good at math. Where does that come from? Is that really inherent to the brain somehow? Certain people are wired that they can think of it in this logical sort of progression that involves mathematics, where others may have more trouble with that and maybe needs visual cues and geometry to kind of visualize things, where others are more on a different plane. I wouldn't say a better plane, just a different plane, where this abstract notational thing, they get it, if you like.
yeah, it's just the eternal question, right? It's the kind of
Is it
I feel
nature or
like there's like
nurture?
some sort of like a taboo against saying that anything is like innate amongst people and that we're not all like perfectly blank slates. But like I think it is a disservice to your fellow learners if you pretend that it's as easy for everyone to do everything, right? Like I
Right.
remember being in math classes and like I'm not trying to say like I'm like the best mathematician ever, but I remember taking math classes in college and having people like tell me about how much they were studying and how hard of a time they were having. And I remember like in some of those classes I was like, yeah, me too. And in some of them I was like, this is just really not that bad for me. Like I actually don't understand how that is. And like it seemed mean to pretend that like, you know, you were having a similarly like that. Oh no, like I got an A. Like you must just not have studied hard enough. Like no, like I did good on that exam and it wasn't that hard. Like, and I know you studied hard and you didn't do good, but like it's not because you didn't study hard enough, right? Like I
Hmm.
don't know. It sort of feels meaner to pretend that there isn't some sort of gradient in abilities to this because there kind of is obviously with every other task that humans perform, right?
Right.
Like people are better or worse at guitar or basketball, but like yeah, what determines how much better people are at math? And like, my God, some people seem so good at it, right? They're like mutants among us, There have been these titans in history, and it's crazy, and I don't get it.
Yeah,
But
there's
also, a lot of people kind of feel like you can just grind it, right? Like, and I sort of feel that way too. Like people
And
who struggle, like maybe you could just push on and you like cross a threshold and
I I
go
always
past it.
I always called it the golden problem when I was teaching at high school level. And because it may be the first problem for some of us, but it may be the 200th problem for others. But we
Yes.
all have that golden moment where we go, oh, that's why. And you just
Yeah.
sometimes you just gotta struggle for it or figure out, hey, isn't for me. If
Yeah.
it's that 300th problem, maybe this isn't the route you want to go.
Yeah. Yeah. It's just the interesting question of like where do people kind of top out at, where do they
Right.
sort of hit their top at? And I think most of the time that's determined to some extent by interest and motivation, right?
Hmm.
um but you can imagine like if you had some sort of perfect incentive system, like some the horrible punishments will happen to you if you don't learn this thing and like the best possible things will happen to you if you do. Like most people could do most of it, right? Like
Right.
everyone kind of feels like that. Like if you're gonna like like calculate this integral, like you have 6 months, like, and it's not even like a hard one. It's like a Calc 1 one, like calculate it or like you die or something. Like most people will figure it out, right? I mean, I don't know. I don't have any data on that, and I hope no one carries out the experiment. But like you kind of feel like it's true, right? Like it's like a pretty algorithmic process for like a lot of things we know. Most people can carry out, like cook, they can follow recipes. Like most people could figure it out.
And there seems to be this
Yeah.
thing. Seems to be this thing in math, which you don't see it as often in, let's say, the normal subjects that are taught in middle school, high school, and so on. Is in math as you progress along. There's at one point where you run into algebra, and that seems to be a bit of a wall, right? It's almost like at that point it's basic training, right? You look around, and then the two people on either side of you won't be here at the end, type of thing. So there's that.
Yeah.
There's that issue, and then the next one that kind of hits is when you hit calculus.
Calculus.
And that's another roadblock for people. So are these almost well-defined subjects in mathematics where you just start leaving, a significant fraction of the general public, if you like, behind? Mm-hmm. And I wonder if that. I mean, you mentioned that if there was a strong motivation, we probably could do it. So do people look at it and say, this is going to be more difficult than what I want to really put the time in, so they lose focus?
I think that has something to do with it. Yeah. Similarly, I often ran into students had never had pointed out to them that 3/4 is just 3 divided by 4. They don't understand this conflation of notation, that it all means the same thing. It's just different ways of writing it. And, that just blew students' minds when I was teaching algebra in high school. Is they'd be like, whoa, wait, what? Yeah.
It's wild how you could identify these things. Like I was teaching like a remedial summer math course, like quite a number of years ago now. And I had this one student who was just like doing very bad. And it was like the lowest level math course offered. And it was during the summer, like they were taking nothing else. Like they had nothing but time to focus on this. And they were trying so hard. They were coming to all of my office hours, like just using up like I was kind of becoming like, I like to help out, but also I was kind of like, oh my God, I've spent like so much time helping the student and we're not making any progress. Like I'll explain something and then I'll ask them like, so A is B. So here, what do we have? And they'll be like A, and I'll be like, so what is it? And they'll be like, D. Like, no, like so close, right? And we just like could not connect the dots. And like I remember just like talking to my wife, who's girlfriend at the time, and I was like, I don't know what to do in this situation. Like this is crazy, and like she's like, I don't know, like maybe like it's just too much. And we kept working or whatever. And at some point, I realized that they did not understand what the equals sign meant, which seems like a weird thing not to understand, but they were like not using it correctly. They didn't really understand where it should be put. They thought like I was like, but wait, why do you think that equals that? Like, and they were like, well, like they basically said something along the lines of me like, well, no, but that's what you write, like to indicate essentially that you're performing mathematics. Like you write that at like the beginning of a line. Sometimes you can write it at like somewhere. And like it was kind of a strange misconception that I like really never seen before, but they were like fundamentally confused about its role, and they were sort of sprinkling it in places like it did not really belong.
Like a comma.
And like yeah, right? It was sort of strange. And we sort of like worked through that and like talked about how to do it. Like, like it's like it basically means is, like, and then that person went on to do pretty well in the rest of the class and take more classes and eventually got a math major. And then, as far as I know, is still working on their PhD in math.
Nice.
And it's doing like good.
So
it's like a crazy flip from like, I can't teach you anything to like, you're doing really great, actually. And yeah, there can be these like tiny low-level roadblocks.
And we're getting some comments of the current education system is broken and like the $ sign in LaTeX.
Well, I mean,
you know,
you can look at the math scores around the world and judge for that for yourself. You don't have to guess.
right.
How well does the United States stack up against other countries when it comes to mathematical ability at
And-
different grade levels?
And the answer is it's been pretty steady, but it's abysmal.
Yeah.
So,
Well,
yeah.
I have seen things that like if you try to like look at other countries and stuff, if you like adjust for various factors, it's like not as bad as you may
Oh,
like expect. That there's like relatively like similar performance amongst like similar like cohorts in
Right.
various places.
well,
And this is like another thing I would love to know if you guys feel the same in physics, is that I've noticed that like there's a degree to which people's enthusiasm and enthusiasm for and enjoyment of a class is strongly influenced by their instructor. But
Yes.
like overwhelmingly, I've noticed that I don't think that there's like after a certain minimum level of instructor quality, like it does not seem that there's that big of a difference in pass and fail rates in classes. If they're okay, you're gonna get like not that crazy of a difference in pass and fail from like exceptional.
and I will agree and disagree. What I think the thing is it's the enthusiasm of the instructor that oftentimes makes the difference.
Yeah, totally.
It's not necessarily even their instructional ability. It's how enthusiastic they are about the subject. I noticed that and even went to the point of telling students that were in my education majors, I was like, if you have no enthusiasm for it, how are you going to make your students excited about this course? And
Yeah.
so there is a certain bottom level, base level of instruction ability you need to have. But after that, it's enthusiasm. It's showing up and saying, this stuff is cool.
Yeah. It's remarkable how many people get jacked up about a subject and then go on to teach it. And after they've taught it like a couple of times, get so bored of it that they like don't like
Right.
it anymore. And like it just shows to their students.
And I've got a comment that I've got to address because I know some of the answer to this. The comment was, oh, if you tweak the variables and perspectives, the outcome isn't as bad. This sounds like statistics. It does, but it's not. There are certain education systems where unless you do well enough on tests, you don't go on to our equivalent of high school. You are shunted off into other programs. And if you take into account things like that, which is, I think, what you were commenting on, and compare apples to apples, we educate everybody no matter what their ability. And other countries do not. They absolutely do not do that. So, of course, you've got the best in math going on to study math in those countries.
Totally.
And comparing our system to that, 1-to-1 is apples to oranges.
Yeah.
And
it's
that's
not
more
the-
what we're
you're not
talking
comparing
about.
amongst the same cohorts. Yeah.
Right. So you've kind of got to normalize the system using math speak so that you are comparing the same things.
Yeah.
So-
I mean, and statistics is a perfectly reasonable way to try to get at some of this. Yeah.
Yeah.
Absolutely.
And the other thing we run into a lot is that some students, and depending on the level you're at, don't see any practical use of mathematics besides, the basic minimum type of thing.
Right.
They're like, what is this good for? Why am I learning this? What will it make me do my taxes rather than getting someone else to do it?
And-
This kind of stuff.
And the answer is usually yes.
Yeah.
It will help you do your taxes, but
But you always run into that
To some
roadblock,
extent, right? We can all type the boxes into TurboTax, right? You know,
Yeah.
like,
Yeah.
It's a good question. Like a lot of people, do they need math? And I mean, I know I teach math and I'm supposed to say yes, but I often think about that. A lot of people don't use it in their life. So how much can they need it? Right?
right.
Like there's all these kinds of arguments like, well, your life would be better if you used math, but that's a different argument than do you need it, right? Like my life would be better if I was a skilled carpenter and could build my own furniture, like for the price
Right.
of raw lumber, but I can get by fine without it, right? Most people can. Like,
Yeah.
it is interesting. There's a very strong utility in some level of numeracy, right? You know, everyone's got to balance their budgets and stuff, or to some extent. I mean, people don't, but like you get finances to some degree,
Yeah.
or you get in big trouble. But
And
man, you can just be fuzzy logic with that and be okay.
we're getting now some comments about that sometimes the best way to teach things
I
to
think
the average person.
you just cut out.
Oh, can you hear me? Oh, Lordy.
Can you hear me,
Uh-oh,
Bryce?
I just lost sound from you right there. What just happened?
I don't know. Can you hear us again? I'm guessing not because you're not responding. Goody. Everything seems to be okay. So let me try this. Yeah, we're having technical difficulties here, folks.
Technical difficulties beyond our control. Now we need math to figure this out.
We need something.
Okay.
I can hear you, Bryce. Can you hear me?
Well, I try to figure this
Let
out.
me try something.
Well, we can hear him anyways.
Yeah, we can hear him. We can.
He just
let
can't
me
hear
let
us.
me type something to him.
It's on my end. I'm sorry. I'm fixing this. Here.
Okay.
Okay.
I got you. I know what's happening.
Can you hear us?
Okay.
Can you hear us?
Yes, now I can. I
Okay.
apologize for that. My speaker stopped working. Weird.
It's okay.
Yeah. So
Okay.
getting back to the practical use of mathematics. Obviously, if you're in a trade like being a carpenter, then ratios, Pythagoras theorem, all these
Yeah.
kind of things are extremely important.
Right. Except they're important to a point because you've got tables that tell you, you know, if your rise on the stair is this, here's what the run needs to be, and things like that to get this pitch. And so people then still ask, why do I need to know how to do this when there's a nice table I can consult?
Yeah.
And
And
I get what they're saying, but at the same time, I'm like, because sometimes you may not have immediate access to that table, but you still need to do something.
And then of course today
So-
we have lasers.
Yeah.
So if you want to know how
Yeah.
long to cut a board, right? There's a laser that'll tell you that. You
Yeah.
know,
That's true.
Measure twice and cut once, as they say, right?
So, you know, and I got to admit, I'm pragmatic about that. I'm like, you know, use the tools you have
yeah.
available. But at the same time, there does need to be a certain level of you hit the nail on the head. There does need to be a certain level of understanding and numeracy involved. Otherwise, we reach a point where people know what to do, but they have no idea why they do that.
Well, I mean, and that's so many different things. So many people feel
Yeah.
like that. Like most people, like, I don't know, right? Like no one understands where anything comes from or how it's made. I mean, no, you know, right? Like ask a random person on the street, like how do you make steel? And they won't describe to you like, you know, like the Bessemer process or something. They'll they kind of shrug. I don't know, right? Like it took people a long time to figure that out.
Right.
Yeah, but no, I don't know. There's all these kind of arguments of like, why do people need mathematics? And I don't know 100% if it's the case that most people need more than a very relatively low level of mathematics, like kind of some basic arithmetic or like vague awareness of the existence of algebra. Like
Yeah.
some people need to know mathematics. Otherwise, everything falls apart, right? But
Right.
does everyone need to know mathematics? I don't know.
I mean, I've often said that people do need, for the very reason that's came up in the chat. There is a certain basic level of statistics that very few people, at least in America, know that everybody should know, so that you can tell when you are being lied to by statistics. Because
Yes.
you know, statistics don't lie. The people using statistics are the ones who lie.
Oh yeah, yeah. I mean, it's far easier to convince people of things if you can sort of lean on the authority of mathematics, which people
Right.
are used to, you know, going like, well, I don't understand it, but apparently I'm wrong, right? That's
Right.
most people's experience in a lot of school. It's like math gets thrown at you and you go like, well, I guess I'm wrong. Like it's pretty easy to use that to justify your argument inappropriately. And yeah, people love to do that.
People love to do that. And if there was a basic understanding of statistics, you would know when somebody's trying to pull, you know, n equals 3. What? You're trying to
Yeah,
make a
yeah.
statement when your sample size is 3?
I mean, that's extremely important nowadays if you just look at elections.
Right.
And I'm not going to say which side of the political aisle I support, but people, and then it happens on both sides anyways here in the United States, that people
Yeah.
will do various things. Just look at the polling, for example, right? Here is the results.
yeah.
This person's ahead by 1%. 19 times out of X, right?
Right.
They do, and what does that even mean? Do you have a gut feeling for what that means?
And-
Because that can actually sway voters, right? We always hear
It
the
can.
case where, on voting day, people will not go to the polls because it may be very inconvenient. But if they hear that, or they think that somebody is way ahead, that there's no reason that I need to go because what's the point?
Right.
Then they won't go.
Oh yeah.
Or you can just look at like the case with vaccines, for example. If you want to, I'm not going to go down that rabbit hole, but think of COVID vaccines.
it. Yeah.
Did they actually help at all?
Right.
Well, all of the
Yeah.
all of the medical journals, like New England Journal of Medicine, have several articles there about the effectiveness of the various vaccines that were made, and it's all statistics. Out of this sample group, this happens, this percent, and if you have you sort of a blind study and this kind of thing, this is the percent that you get, and so you have to know what that even means intellectually to get the information out of that,
And
not rely on others to say, well, this is what it really means, even though it may not be correct.
right. Because but that's why I threw out the N number, because so many of the ways statistics can be made to lie involve, lying about or overemphasizing your sample size. And
Oh yeah.
If you don't know that, ask that question. Well, what is your sample size?
Yes.
A lot of these arguments, political arguments, let's say, maybe they should be backed up on both sides or any side. It could be n number of sides with facts so that everybody can see the numbers themselves.
Well, that wouldn't do anything because, we could talk about psychology now, and
Well,
people aren't
let's see
swayed
the
by
data, right? Where does
by
your
data
opinion
arguments.
come
They're
from?
swayed by emotional arguments.
Well, where's the support
It's true.
for what you're saying, right? I mean,
Yeah.
as a scientist, of course, I'm biased into thinking that way.
Right.
But I want to see the data. Just don't tell me that this implies a certain thing. Let me see the hard data so I can make
tell.
that judgment myself.
Right.
Yes, yeah, exactly. I mean, that's probably the main role that teaching people mathematics and statistics can do for you, right?
Right.
Is that like it allows for dispassionate presentations of available information, and then allows people to draw their conclusions on their own. While if you don't have this, then there's like almost like a priestly class of math understanders that
Interpret everything.
yeah, we're all trusting to read the sacred scripts of the studies, it is an unfortunate and in many ways very difficult to resolve problem, right? Many things in the world are profoundly complicated.
Right.
Shockingly so. No one can really get it all. Like maybe some person in the world can understand everything, but no one's got the time for it, even if they can. And so we all have to kind of rely on each other to some degree. We all have to make arguments that are not that are appeals to authority, right? We can't. No one can check everything, right? We can't go from first principles on every possible question that you want, and so the question is, how many people should be checking it? Which, again, feels like something we could actually probably answer, but then I guess we'll have to rely on the priestly class to tell everyone that that's the right answer.
Right.
It is a weird one.
Let's be honest. That's part of what we're doing right now is we're trying to bring out, hey, this is why these are good ideas and these are bad, with our communication show here.
So, Bryce, what's to change it a little bit, what's your feel for the need for mathematicians in society today?
Ooh,
Is
it's
there
a good question.
like a lack of people going into mathematics and there's a great demand? Or is it like you're kind of saturated with mathematicians, we don't need any more, thank you very much?
Well, it's okay. So there's two different answers to it, right? Maybe even three. So there's two answers. There's two kind of questions. Like, does the world need more mathematicians? Does that mean would the world be better if there were more people who are like active practicing mathematicians understanding what it was, right? The answer is, I think, almost undeniably yes. The question is whether or not the world is actually like economically demanding that many more mathematicians, right? Like if we create more of them, are there actually positions where they can go on to study mathematics and use or even just employ the mathematics, that others discover or have discovered using their familiarity with the subject matter? And I think at present, the answer is broadly yes, that there is demand for them still, but not necessarily in all of the fields that people who go into mathematics studying it want to do, right? There's not like a super abundance of nice tenure track positions, teaching and stuff like that, right? Like if you want to just research math all the time for the rest of your life, there is not like a ton of there's not 50,000 new jobs in America for that. There won't be anytime soon, as far as unless we change something very dramatically in a way that I can't even begin to describe how it would occur. But like on the other hand, like if you want to, like we need actuaries, we need coders, like plenty of other things that like if you are good at math, you can probably do.
Data scientists,
Yeah, right. That kind of stuff. So yeah, there's demand for that. Yeah.
Okay.
Hard question.
Yeah, I mean, because you never know, right? Some people might think, well, I want a job at the end of all of these years of studying. If I go up and get a PhD, that's a huge time commitment. So
Right.
is it worth it for me, or should I go off and just get an MBA and try to run a business and make money, I don't know, on the stock market or whatever, or whatever?
Yeah.
Or should I go into some kind of a trade field instead? We're because a lot of people who are still contemplating what they want to do when they get the first year at university,
Right.
and that's
Yeah.
And
That's a good question.
yeah, I mean, I've got an answer there, and it depends on what motivates you. If money is a big thing, then you'd probably be better off going to a trade or something like that. If money is what you're after. If understanding math and math systems is what you're after, you want the PhD in mathematics.
That's right. Yeah, exactly.
And we do have,
yeah.
sorry, go ahead, but we do have a question, but I'll bring that up. You were saying something, sorry.
Oh, I was just going to say, I totally agree. Yeah, if you got to do it for love of the game, it doesn't hurt your earning potential to have a math PhD, but like, yeah, it takes a long time to get one. And that's a lot of sacrificed years of earning and raises and experience, that adds up. I don't know if it's like net and economic positive for most people, especially depending on the area of math you study, but it certainly is fun.
Yeah. And from the Schwalms, we get the question of, will AI change thinking to the extent that there will be a paradigm shift? Math thinking might change profoundly. So in other words, how I think they're getting at how AI, which I kind of agree, I hate that term, but at the same time, it's what's used. Well, how will it change mathematics, I think, and mathematical thinking?
That's a really good question. Yeah. I mean, it just depends, like how already we're at the point where AI and AI-like tools can already do most of the math that we give to undergraduates pretty easily. Most of it. Sometimes, depending on how, like if like the student properly inputs it into the right tools, AI things, or even non-AI tools, like there's reasonable user interfaces now for people to input a problem and get an answer. You can, take a picture of a differential equation with your phone and Snapchat, and it will give you the solution. Sometimes.
Wolf from
right?
Alpha comes to mind. Yeah.
Yeah, stuff like that, right? And so, like, this is perhaps not that big of a paradigm shift in how we think about math any more so than like when we moved from slide rules to calculators. We're just offloading more of the tedious, work to another tool. And in the same way that a lot of like mental arithmetic or hand arithmetic calculation techniques have fallen out of fashion to teach because they're not that important if you can just punch it in a calculator, it's probably fine for some of that to go away and let us like take people to higher levels of math, hopefully not having to focus on some of like the basics quite as much, which might be fun. But the big question is, can we get to the point where like, AI is like replacing actual mathematicians, like proving genuinely interesting, novel new theorems of like, consequence. And Uh, oh, I mean, I personally think that as soon as that happens, like, yeah, we're gonna get to some weird, like, very seismic changes in the world, right?
Right.
Like, that'll be exceptionally strange. I don't know. Yeah. I mean, maybe it turns out that we get computers who can do that, and just suddenly we now know like a lot more math, and it doesn't really cause that much else to change. But I have a big feeling that if we hit that point, it's going to get really weird really quick.
Right.
I mean, when you think of AI, it's it's trained on something,
Right.
so it just does those calculations. Obviously a lot faster than a human being can do.
Yeah.
So it could possibly find things that we missed in our thinking process, logical connections that otherwise we wouldn't know that were there. But is it really doing something novel in the sense that it's thinking on its own? That's the thing I argue.
Well, it's hard to say, like, yeah, what does it even mean, right?
Yeah.
Yeah. In some sense, it kind of goes back to the, like, is math created or discovered or something, right?
Yeah.
Like, whatever. So, I don't know, if you think about it, like, okay, so, like, what are you a thinking being, Like, what is that? It certainly, I would argue, like, I mean, perhaps we go for some sort of metaphysical, like, soul type thing or something, but okay, like, perhaps if we go for that, but if we go for some sort of purely physicalistic perspective, like, you go like, okay, well, it's something going on in your brain, right? But it would be very difficult to argue that, like, whatever is happening is particularly tied to any one of the, for instance, like atoms being exactly that atom, right? Like,
Right.
there's some hydrogen in your brain, and if you replaced it with a different hydrogen in exactly the same place with exactly the same state, like, it would really change anything. Like, they should be kind of like interchangeable parts, so it's the configuration of the matter that is the thinking being, and the configuration is not so much a physical thing as the physical thing is like manifesting whatever the structure mathematically is that the configuration represents.
Right.
Right. And so it's like the configuration like allows like the whatever it is from like the Platonic realm to be channeled into, made manifest or something. Right.
Right.
And so the question is like, are there like, okay, so why would we assume perhaps that only specifically, these types of physical objects in this specific way can manifest certain structures, right? Like certain objects, can have certain properties, Like, I imagine that there are many different ways of making things in physical reality that allow for whatever that mathematical object is to be demonstrated, like made manifest here, right?
Right.
And I don't know, I imagine that you could probably do it with like a computer, right? It doesn't seem too crazy to me. It gets weird when you start to think like, could you just do it like on paper, right? With like no moving parts, just write it down, like. That seems different,
Yeah.
I don't know.
I think we're getting into where, again, drawing on my own experiences, I often told students, you don't have to do it my way. There are more than one right way to do these problems. You just have to do it a right way.
Yeah.
If you find another way that is a right way, but it makes more sense to you, please use that.
Yes.
And that blew, I won't go into how much that blew people's minds. You don't want us to do it this way? It's like, no, I don't.
A classic. Yes.
Yeah.
Yes.
It's like in physics, we're just interested really what is the answer, and do you have the ability to look at the answer and think that it's reasonable or not?
Right. Right.
So if you calculate that the mass of a muffin is 3 times the mass of the sun, you have a little bit of a problem somewhere along the way. And you should recognize that.
You should
and not
recognize
say,
it.
Well, I got to an answer, I'm done. I'm going to move on to do something else. Like, no, look at your answer. Clearly it's wrong. Right? You should be able to recognize that and not be satisfied with just coming down with some number.
I've had that discussion. A student called me over. Does this answer look right? they had an answer for the velocity of a cart moving along a track of 20 meters per second. And I was like, this room is 10 meters long. What do you think? And they were like, I don't know. And I was like, okay, you're saying it went 20 meters per second. That means it went across this room in half a second. What do you think? And then they were like, oh, no, that's not reasonable at all. And I'm like,
probably a little too quick, you know? Yeah.
Yeah.
Classic. But
Yeah.
then again, I feel like that's our fault, because I often come up with example problems and like in like a Calc 1 class or something, and like I won't like it, you know what I mean? Like the story problem type format, like it doesn't really matter what the numbers are. I'm just trying to get you to apply something, right?
Right.
Like do like, you know, like a related rates problem in Calc 1 with like a like sand piling up in a cone or something, and like how fast does the diameter change with respect to the height or something, you know, right? Like these types of problems.
Given an angle repose of
Yeah.
sorry.
But then you have like the like units work out where it's like oh, this like it's changing by 41 kilometers per second. Like it's like, does that seem right? Like, you know,
Right.
it's a pretty big pile of sand. Like, but you know what? If we gave you those numbers that works out for that, like then yeah, it is right. Like we do that a lot where we give them very unrealistic example problems. So that's probably our fault. But
Now, with the time remaining, Bryce, I want to give you the opportunity maybe to say a bit about what you actually do for research in your field.
oh, I mean, sure, yeah.
Yeah.
I'm interested in very broadly, you could say I'm interested in stability in some sense. I'm interested in things settling down in some way. Like, you know, they could behave strangely, and after a certain point, they start to behave less strangely. I'm interested in like, this happens all over the place. So you can think of classic examples, like you've got a pendulum and it swings down to the bottom. Okay, fine. Like that's you know, going down some sort of equilibrium or something, or you could imagine yourself trying to make something stable. You're trying to like balance a broomstick on your hand. How do you move your hand so that it goes back upright and stays there, right? But also these sorts of things happen in other places, like when structures start to emerge, right? Like if you have a small disorganized object, it can be very, very disorganized. But if you have a large disorganized object, if it's big enough, it has to have small organized parts. Like in some sense, many sufficiently large objects can't be completely disordered, which is a kind of weird way to think of things. You might imagine that larger things can be even messier than smaller things, but in some sense they can't. They have to, many objects run out of room to be disordered, and they start to have little ordered chunks pop up in them. This happens all over the place. There's also a lot of different types of threshold phenomena where, like, okay, take a random object, like a large random object that varies based on a parameter. And if the parameter grows slower than something, then the object, like, asymptotically does not have some property. And if it grows faster than something, it just almost certainly does, right? Large enough parameters and like these parameterized families of random objects begin to exhibit orderly structure beyond certain points. There is almost always this notion of stability. That is, like with the pendulum, you can imagine that if you start it in certain places, it'll swing down to the bottom, but if you balanced it perfectly straight up, it would just stay right there. You can't, from that top one, you don't accidentally swing down into the bottom one. You just stay away from the bottom one, right? Maybe the pendulum isn't the perfect example because that's another equilibrium state. But I guess what I'm trying to say is that there's usually some sort of a notion of like, once you cross this line, you fall into the thing, right? And you see this all of the time with, things in the physical world, right? Like once you go over this part, then the ball rolls down the hill or something. Otherwise, it could just sit there. But there's these like boundaries where you move from some other state towards suddenly you're attracted to this new one. Suddenly you stabilize and have a certain property that you didn't before. And it doesn't just happen in physical systems, it happens all over the place. It is a very weird thing, and I want to know more about it. But on the subject of AI, one of the places I find it most interesting for it to occur is with strong lottery tickets, as they're called. So this is a paper a number of years ago that generated a considerable amount of attention. People had been training big neural networks, and then after they did it, they went, hey, a lot of the parameters in here, a lot of the weights in the network are very small. We can get rid of them and they don't really do anything. We might as well throw them away, save ourselves some calculations.
I remember that now.
Yeah, they would prune it. And okay, cool. And some guys recognized, Franklin Carbon recognized that they can prune a network before training in some way with that most networks you could prune some part of it off beforehand and end up with a smaller network that if you trained that in isolation would reach comparable accuracy to the larger network in a similar number of iterations. Some people later trying to prove this, which was called the lottery ticket hypothesis, and the intuition for it was basically that like large enough networks, you are sort of playing like a game of slots, right? Like if you play enough lines, you have a pretty good chance of winning, but if you only play like one line, you probably won't win. The same kind of thing, like the wider it is, the more chances you are to have like a little chunk of it that's pretty close to being the right answer already, or, you know, a little chunk of it that's closer to the right answer and can reach it, you know, in a small number of training steps. Some people later went, well, why are we even training it at all? Do big enough networks have subnetworks that just do as well as the whole thing after training, but with no training at all? And the answer is yes. These are called strong lottery tickets. And so after a certain point, large neural networks kind of, with respect to any given task that you want it to do, neural networks stabilize beyond a certain point and start to almost surely have the ability to do that task like hidden inside of them. Like there's a little piece in there that already does it with no training and you just have to uncover it, which is really weird. There's yeah, it's like you run out of ways to do things wrong. And so you have to have a way to do it right kind of buried inside of it.
Right.
Like it's a weird one, but it comes up everywhere.
We get AI to study itself.
Right.
Yeah.
I was thinking in terms of cosmology and the fact that galaxies then sound like an absolute consequence of having a wide open, chaotic space. You know?
Yeah. Well, I mean, everyone's.
Yeah.
Oh, sorry. Yeah.
Yeah.
I mean, everyone's seen those pictures of like, you know, like, oh, here's like you know, like the structure of connections in your brain, and here's like, you know, like the large scale structure of the universe. Like there's like memes like that like.
Yeah.
You know, people who like crystals, you know, share and stuff, like yoga people, right? But like they maybe have a point. It may be the case that like just, you know, the connections are effectively random because the only thing that matters is that there's enough of them.
Right.
And what goes on is just finding the right piece inside of it.
So, Bryce, you're getting to the sci-fi that the universe is a giant brain that's inside of a living creature. That's
Well, I don't know about that, but I'm just saying, I mean, structure and like an effectively random configuration, and to some extent, like on large enough scales, right? Like maybe most of the learning process is like a search process as opposed to a training process, where you're just finding the right pieces in this large random object.
right. And you could, I mean, you can do a mathematical comparison of that. You can look at like the 1 point, the 2 point, the 3 point correlation function of large scale structure in the universe and compare it to the structure you see in the brain.
Yeah, you could probably actually check it out. That'd be fun.
I mean, that's how we know that the universe is not, that's how we know the universe is not fractal in nature, which is one of the big push early on, you know, with chaos theory when that all came along in the 70s or something. And then people tried to apply that, right? But that was looking at incomplete sort of sampling of the universe at that time. But now we've probed depths much greater and have a fuller understanding of the three-dimensional structure, and it's certainly not fractal in nature, the universe.
Which is cool and weird. It's weird that there's like an end to structure. That,
Yeah.
you know, at some point it just homogenizes.
For sure. Anyways, we've come to the end today.
We've
and
come to the end.
Thank
It's
you
been a
very
good
much,
discussion.
Bryce, for a
Thank
great
you.
discussion. Yes.
Yeah,
And-
thanks for having me. This is great. I had so much fun.
Great. Our next podcast will be next Tuesday. That's April the 22nd. If you're interested in math, this is a plug for
Right.
Bryce. If you're interested and you want to study math here at the University of North Dakota, you can come on campus. There are lots of courses that you can take, plus online as well.
Mm-hmm.
And so, then if you math is like, you know, a sideshow for you, there are other higher education programs that we have
Right.
here at the university as well.
How to talk about math. Communicate it.
Exactly. All of these things are extremely important. The other thing we do at the end of our podcast is we leave you with a quote.
Yeah. Okay.
And this quote,
I'm betting it's a mathematician today.
it's a quote from Bryce. No, just kidding. I just wrote down what he said at the beginning of the podcast. So actually, it's a quote from Leonhard Euler
Euler. Okay.
from the 1700s. And here's what he said. He said many things, but here's one of the things that he said. Mathematicians have tried in vain to this day to discover some order in the sequence of prime numbers, and we have reason to believe that it is a mystery into which the human mind will never penetrate.
Interesting.
If you like this podcast, please remember to give us a thumbs up, and thank you very much for watching.
Thank you, folks. Have a good evening.
Thanks, everyone.